Cosmologists can trace the evolution of our universe back 13.8 billion years to the Big Bang. But the Big Bang itself is an event still shrouded in mystery. In this series, we explore competing models of the early universe. While cosmologists may disagree as to the true nature of the Big Bang, what they do tend to agree on is that when the entire observable universe is far smaller than an atom, the strange world of quantum mechanics surely becomes relevant. At Cambridge University, one of the first attempts to build a cosmology based on quantum theory was pioneered by Stephen Hawking, Thomas Hertog, and James Hartle. Their theory is known as the no-boundary proposal. In this episode, they'll explain how their no-boundary proposal may be able to tackle some of the deepest mysteries of our existence. From why is there an arrow of time? Or is there a multiverse? And how do we resolve the Big Bang singularity itself?
Roger Penrose and I showed on theoretical grounds that if Einstein's general theory of relativity is correct, there must have been a singularity in the past, a point of infinite density and spacetime curvature, where time has a beginning. However, although our singularity theorem predicted that the universe had a beginning, it didn't say how it had begun.
The singularity theorems, Penrose, Hawking, and others, showed gravity would become so strong in the beginning that the classical physics would break down. That meant that quantum physics was inevitably going to be important.
The idea to use quantum cosmology to understand the origin of the universe goes back way before Penrose and Hawking. In fact, it came along with the discovery of the expansion of the universe. So even in the 30s, people began to ask the question, well, what happens at the origin of the universe? And the suggestion was made back in the 30s that at the very early phase of cosmology, in the very early phase of cosmological evolution, quantum theory would come into play. But of course, in the 30s, the tools were not available to say anything about the origin. This was just an idea for an idea, as John Wheeler would have said.
The initial singularity theorems developed in the 1920s by Friedmann and Lemaitre had the unreasonable assumption that the universe was perfectly symmetrical. In the 1960s, Penrose and Hawking developed new singularity theorems that did not require this premise.
So in the early days, you could have said, well, the initial singularity, the initial Big Bang singularity, is a feature of very specific universes. But Penrose and Hawking showed that, in fact, this initial Big Bang singularity is a generic feature.
The real lesson of the singularity theorems is therefore that we need to combine the general theory of relativity with quantum theory in order to understand the origin of the universe.
In the 1970s, Stephen Hawking discovered that when quantum theory is applied to black holes, it causes them to evaporate, giving off what is now known as Hawking radiation.
Stephen and Jim both realized that if quantum theory has such a big effect on the singularity inside black holes, presumably it also has something to say about the cosmological singularity.
It was at a conference in the Vatican in 1981 that I first put forward the suggestion that maybe time and space together formed a surface that was finite in size but did not have any boundary or edge. Together with James Hartle from the University of California, I worked out what physical conditions the early universe must satisfy if spacetime had no boundary in the past. Our model became known as the no-boundary proposal. It says that when we go back towards the beginning of our universe, space and time become fuzzy and cap off, somewhat like the North Pole on the surface of the Earth.
In the singularity, the Big Bang is a moment of infinite density and curvature. But in the no-boundary state, there's a smooth surface, which, although finite, does not have a single point of origin.
The key concept is the idea of a wave function, that sometimes a particle can act sometimes like a wave and sometimes like a particle, a photon say, right? When it's acting like a wave, it's described by a wave function.
The no-boundary proposal treats the universe quantum mechanically, and therefore the mathematics needed to describe this strange quantum world will be needed for the universe as a whole.
And the starting point to do this is Richard Feynman's sum over histories formulation of quantum theory. So unlike the Copenhagen interpretation of quantum theory, where you have an external classical world, in Feynman's sum over histories formulation, everything is part of the system. It says essentially that if a particle goes from A to B, it doesn't follow a single history, but it follows all possible paths connecting A to B. Just like in the famous two-slit experiment of quantum theory, where you have a particle that goes through both slits, and the superposition of paths.
A path integral assigns a weighting, or relative probabilities, to different possible histories of the universe. The no-boundary proposal is a selection principle that selects the subset of histories of the universe that close off in the past, and so allows us to determine which histories of the universe have the most significant contribution.
The most significant contribution will come from a geometry that is Euclidean on the bottom of the shuttlecock and an expanding de Sitter universe on the top of the shuttlecock. What I mean when I say the geometry is Euclidean is it has 4 space dimensions and no time dimensions. What I mean when I say that the geometry is Lorentzian is it has 3 space dimensions and 1 time dimension, just like the geometry we experience every day in this room.
The no-boundary proposal is a model of the Big Bang that is based on quantum gravity. It is given by the path integral over all Euclidean metrics, without boundary. By contrast, the Hawking-Penrose theorems are about Lorentzian spacetime, which has a boundary at the singularity.
To describe the wave function and its superposition, physicists use imaginary numbers. But what are these imaginary numbers, and why are they so important for the no-boundary proposal?
Well, imaginary numbers are numbers which square to something negative. I is an example, and I squared is -1. The no-boundary wave function describes or assigns different probabilities to different histories of the universe. And it does so by associating each history to a geometric construction, the famous shuttlecock construction, in which a history is in fact rounded off in imaginary time. In this context, when we say imaginary time, the no-boundary proposal, we are really talking about geometries in which time behaves as a space direction. The no-boundary proposal does not describe a single history for the universe, but it describes an ensemble of different histories.
The past is probabilistic, just like the future. It's symmetric.
So in that sense, it is similar to a wave function of an ordinary quantum mechanical system, which describes an ensemble of different histories or paths, just like in the two-slit experiment.
So if that's true, then there must be a wave function for the universe. And the question is, what is it?
So this is the formula for the no-boundary wave function. What does this mean? The no-boundary wave function the no-boundary wave function gives you an amplitude, a weighting for different configurations at some moment of time, different kinds of universes. You could think of each h and phi as a universe. The amplitude of each universe, according to the no-boundary wave function, is given by a Euclidean path integral. There is no notion of time at this level. Time does not appear in this formula. Now there's a special condition, the no-boundary condition, which asserts that those histories contribute to the path integral which have no other boundary except the one at which you're evaluating the wave function. And that's what leads to that shuttlecock picture. How am I going to draw a geometry which has no other boundary than the boundary at which I'm evaluating the wave function? I naturally draw something like this, right?
So these shuttlecock geometries, they are geometries, complex geometries, which start out with all dimensions behaving as a space dimension.
This region, which is Euclidean, and where all dimensions behave as a space, changes. The spatial dimension remains a circle, but the time dimension opens up and becomes distinct from the space dimension and describes a universe in which a spatial circle grows and grows and grows. I can no longer interchange time and space here. This is the way time, Lorentzian time evolution, emerges when the universe gets larger from what is initially a quantum fuzz.
Classical physics is not fundamental, it's an emergent phenomena, we believe, from a quantum mechanical theory.
The notion of classical evolution emerges from the no-boundary wave function when the universe gets sufficiently large. According to the no-boundary proposal, the only way to get a classical universe with a deterministic notion of time is via a period of inflation.
Inflation is a period of incredibly rapid cosmic expansion, believed to have occurred in the early universe. Inflation is thought to solve a number of problems with standard Big Bang cosmology, and it's driven by a form of matter known as a false vacuum, which causes the expansion to accelerate instead of slowing it down. When this form of matter decays, inflation ends, creating a hot soup of particles.
The no-boundary proposal explains how inflation started and it's a very large, ununiform universe, just as we observe. However, it would not be completely uniform, because in the Euclidean path integral, histories that are very slightly irregular have almost as high probabilities as a completely uniform history. The theory therefore predicts that the early universe is likely to be slightly non-uniform. This produces small variations in the intensity of the microwave background from different directions. Some regions will expand slower than others, which eventually leads to the formation of galaxies. Detailed observations have confirmed there are indeed changes in the intensity of the radiation at the level of about 1 part in 100,000. Moreover, the observed pattern is in excellent agreement with the predictions of inflation, combined with the no-boundary proposal.
The standard theory of inflation predicts the generic features of the primordial fluctuations, but it doesn't predict the details. There are all kinds of inflationary universes. You need the no-boundary wave function, and in particular the probabilities that it predicts for different inflationary universes, in order to complete the theory and make specific, sharp predictions.
The predictions of the no-boundary proposal will be a combination of the probabilities given by the no-boundary wave function and the possibilities coming out of the dynamical model of the earlier. It's the two combined which lead to very specific predictions. Now, of course, we don't have a complete theory of the dynamical model, so we are not sure yet what are the possibilities. But in a specific corner of the string landscape, the corner described by deep brain inflation, that is a regime, that is a model of inflation in string theory in which the accelerated expansion is driven by the motion of a membrane through an extra dimension. Within the context of that dynamical model, the no-boundary wave function will make a very specific prediction for things like the tilt, so for the spectral features of the pattern of microwave background fluctuations, such as the contribution from gravitational waves and the tilt and so forth. But I don't like to stress those predictions precisely because of the uncertainty on the dynamical model. What the point of our program on the no-boundary wave function is to demonstrate that if you have a dynamical model for the early universe and you have a theory of its quantum state, the two combined yield a predictive framework for cosmology. In other words, the two combined turn multiverse cosmology into a proper, verifiable scientific framework.
The goal of cosmology is to construct a model of the universe that makes falsifiable predictions that can be tested by observations.
And to falsify the no-boundary wave function, you would have to identify correlations that are impossible within the theory, such as, for instance, spectral features of the primordial perturbations, which are incompatible with inflation.
So for a long time it was thought that the no-boundary proposal predicted essentially an empty universe with just a little bit of inflation. However, that prediction is what we now call a bottom-up probability of the no-boundary wave function. It's a probability which you derive straight from the wave function and which does not take into account the condition that we actually exist in the universe. When it comes to testing the no-boundary proposal against our observations, we first must include the condition that we are part of the universe, that we are part as a physical system of the universe. That condition, so in other words, we have to calculate a conditional probability in order to compare the predictions of the no-boundary proposal with our observations. It turns out that this condition has a large effect on the probabilities predicted by the no-boundary proposal. Without this condition, the no-boundary proposal predicts just a short period of inflation and an empty universe. But when our observational situation is taken into account as part of the universe, in fact, the most probable histories of the universe that are predicted by the no-boundary proposal are histories with a long period of inflation and, when extrapolated backwards in time, in fact, with a phase of eternal inflation. And the reason for that is simple. In these first class of histories, which has just a little bit of inflation, they're smaller. They don't have many places for us to be. Whereas the histories with a long period of inflation, they're much bigger. They have lots of places for us to be. And since we are a physical system within the universe, with a certain probability to be anywhere, we are much more likely to be in one of these large histories than in the small histories. So in other words, what's most probable to be is not necessarily what's most probable to be observed, precisely because there are more places for us to be.
What temperature we will observe for the microwave background? That question doesn't make any sense because it doesn't say what time we look at it. So you need to distinguish between predictions for whole histories of the four-dimensional histories of the universe and predictions for our observations of it, which are typically at one moment of time. That difference between the two kinds of probabilities, probabilities for observation and probabilities for the whole history of the universe, I think capture a large part of the difference of what's meant by top-down and bottom-up.
It turns out that the top-down probabilities given by the no-boundary proposal predict that we have a long period of inflation in our past. and therefore we predict a flat universe. In fact, we predict a universe with so much inflation that it has a period of eternal inflation.
In our previous film, Alan Guth, the father of inflationary theory, claimed that inflation is generically eternal. In other words, almost all models of inflation lead to a multiverse.
The multiverse arises in inflation from the same quantum mechanical effect that leads to the irregularities in the early universe seen in the microwave background. This is because if one traces the universe's history backwards in time, deep into the face of inflation, one can encounter a regime of eternal inflation. In eternal inflation, the quantum fluctuations in the energy density of the matter are large. It is usually thought that this can keep inflation going forever in some regions of the universe. Our observable universe would then become a local pocket universe, a region in which inflation has ended. Globally, the universe would have a highly complicated structure and would consist of infinitely many such pocket universes, separated from each other by inflating regions. The local laws of physics and chemistry can differ from one pocket universe to another, which together form a multiverse.
In general, in quantum mechanics, there's always a multiverse, because quantum mechanics doesn't predict one thing, it predicts probabilities for things.
And the conventional way of handling eternal inflation has led to paradoxes. Eternal inflation seems to produce an infinite number of each kind of pocket universe. So what should we tell the observers as to in which pocket we are? That problem clearly shows that the conventional theory of eternal inflation is incomplete. The reason the no-boundary wave function is a completion of the theory of eternal inflation is that it predicts an ensemble of eternally inflating universes with a probability measure, with a probability distribution over that ensemble. That probability distribution allows you to extract probabilities, relative probabilities, for one pocket universe versus another. And it's those relative probabilities which are the key quantum mechanical prediction for what we should observe.
A number of scientists have claimed that many features of the universe are delicately fine-tuned. One example is the initial conditions for inflation.
So the boundary wave function is a solution for the problem of initial conditions for inflation. It's often thought that an inflationary universe requires very special initial conditions. But the no-boundary wave function selects those universes which have a period of inflation. So the initial conditions for inflation are not fine-tuned in the no-boundary wave function. In fact, inflation is precisely what the no-boundary wave function predicts.
In 1998, scientists discovered the universe is accelerating in its expansion, perhaps being driven by a repulsive gravity term invented by Einstein known as the cosmological constant. This, too, has been claimed as a case of delicate fine-tuning.
We need to deal with it from this top-down or first-person point of view, right, in which we're asked not what is the most probable value of the cosmological constant, but what's the most probable value of the cosmological constant that we can see. The reason is because, as explained by Barrow, Tipler, Weinberg, and others, if the cosmological constant is too big, the universe expands too rapidly, and then based on calculations by Tegmark, Rees, and others, right, galaxies wouldn't form, and we wouldn't be here to see what's going on.
In a multiverse, you will naturally have different values for constants of nature in different universes. A famous example is the cosmological constant, which can take different values.
We could, for example, have a universe that eternally inflates by a cosmological constant, and within that universe, that false vacuum, as it's called, would decay by bubble nucleation, and we live in one of the bubbles right? That's already a multiverse. Quantum mechanics generally predicts probabilities for ensembles of histories. That's a multiverse. If the dynamics permits the cosmological constant to differ from one of those histories to another, we predict probabilities for the value of the cosmological constant.
So those constants of nature in classical cosmology, they're just numbers without any explanation. In quantum cosmology, you can hope to explain those numbers or to explain at least certain correlations between those numbers from a deeper underlying theory.
Let's come back to this universe that has a false vacuum that's expanding, but also decaying by nucleation of bubbles of true vacuum. If you run that forward for any bit of time, you get a very complex structure, a roiling sea, so to speak, of bubbles. That's very difficult to calculate. In fact, it's so difficult that people assume for the minute that there's only a finite number of them and then try to let the number go to infinity. That's called a measure.
Calculating probabilities in an infinite multiverse is no easy task. It requires a counting procedure known in mathematics as a measure. But there's no agreement among physicists as to what measure to choose. Is there another way out of this measure problem?
There's a simpler way of doing it, which is this first-person top-down idea that you should focus on just what it is you observe, one bubble, right? And ignore all the other bubbles. And there's a way of doing that in quantum mechanics called coarse graining.
To me, fine-tuning is a top-down question. It doesn't mean very much to say, well, the theory is wrong because it predicts some universe which we can't observe. To me, the real question is whether the constants of nature that we observe, given we exist within a universe, are likely or not. So 10 years before the cosmological constant was discovered, Steven Weinberg pretty much predicted its value based on this kind of reasoning. That reasoning is pretty much automatic in quantum cosmology because we are very much physical systems within the universe in this theory. We're part of this final configuration. So the real question is whether the no-boundary wave function predicts correct correlations between our existence and the observed values of the constants of nature. And if we do this for the cosmological constant, for instance, in the no-boundary wave function, we're actually able to sharpen Weinberg's predictions precisely because we have a more definite theory of initial conditions. That's the way the no-boundary wave function can be tested against observations and so forth. Of course, this may not work or agree or for all constants of nature. We're not even sure that all constants of nature can really vary from one universe to another in the multiverse. But those constants of nature which can vary can be predicted using this kind of method. For the other constants, I don't really know. Some of them might be determined by the theory. So in a way, they might be necessary.
It's easy to get the cosmological constant to vary with an appropriate dynamical theory. I think we don't know whether other constants are put in or vary. You have to have, in other words, to say that there's anthropic collection, fine-tuning, and you have to have a mechanism for the constants to vary and not simply be fixed by the fundamental theory.
Critics of the multiverse have said that as other bubble universes are not observable, the multiverse is not science.
Well, I think that's rubbish. Physics always involves concepts and ingredients which are not directly observable. An example is the Higgs boson. We don't observe it directly. We observe its decay products. All theories in physics have ingredients and concepts which are not directly observable, but play a role in deriving predictions for features which are observable. Similarly, so for the multiverse. My goal, or the goal of the program of the no-boundary proposal, is to turn the multiverse into a verifiable, falsifiable, predictive framework. How do we do that? Well, we use this multiverse to derive predictions for observations in our universe. So, of course, it's true that we're not going to be able to observe wildly different universes from ours, but we use the entire framework, we use the entire multiverse, we use the ensemble of histories to extract predictions for our universe. So in that sense, it's not fundamentally different, I think, from what is happening in other branches of physics.
The second law of thermodynamics tells us that a random fluctuation of something very ordered is incredibly unlikely, but it isn't impossible. Ludwig Boltzmann, one of the fathers of thermodynamics, wondered if our entire universe might be just such a rare fluctuation. The problem is, a brain would seem more likely to fluctuate than an entire universe. So some have argued that these Boltzmann brains would dominate the multiverse and hence disprove its existence.
Well, Boltzmann brains would be a problem even in a single universe. If a history continues to expand, for instance, because there's a cosmological constant, you create infinite volume and eventually Boltzmann brains will appear. Therefore, Boltzmann brains are not directly associated with theories of the multiverse.
One issue is whether those fluctuating brains in the far future, in an otherwise cold and empty universe, represent in fact fluctuations that decohere. In other words, represent branches, branches of the wave function to which we can assign meaningfully a probability. We have to be able to assign meaningfully a probability in order to draw any conclusions about whether or not we are more likely to be a Boltzmann brain. I think it's far from clear that those kind of fluctuations, in fact, decohere.
Jim, Thomas, and I have recently studied eternal inflation from a different viewpoint. Our approach is based on the concept of holography in string theory. Holography says that Einstein's theory of gravity in spacetime is equivalent, or dual, to a theory without gravity that is defined on the boundary of spacetime. We have used holography to excise the phase of eternal inflation in our past and replace it by a dual theory defined on the global exit surface from eternal inflation. One can use a dual theory to calculate more reliably the global structure of the universe produced by eternal inflation. We find that the probabilities for highly complicated universes are much lower than what the old theory of eternal inflation indicated. This raises doubts about the widely accepted idea that eternal inflation gives rise to an infinitely large multiverse. Instead, we conjecture that the end of eternal inflation is reasonably smooth, leading to a much simpler universe, which is globally finite.
What we find is that even though there can be a phase of eternal inflation, the late-time universe is smoother than what the traditional calculations suggest. So now you might say, well, where is the multiverse then? If my universe is smooth, then it seems to be pretty much the same everywhere. But remember that the no-boundary wave function is a function of the late-time configuration. Therefore, the multiverse is still in there. The no-boundary wave function describes or assigns probabilities to different kinds of universes. It's a multiverse not consisting of pocket universes in a single space-time, but it's a multiverse consisting of an ensemble of different universes. Okay? More quantum, if you like.
All theories are approximations. In order to move from interesting proposal to something widely accepted, a theory must be precise enough to allow for unambiguous predictions. So what must quantum cosmologists do to achieve this?
We must find a better way to define that part integral. This shuttlecock construction is really an approximate construction. It's an approximation of this part integral which has never been defined mathematically precisely. So that's where holography comes in. Holography provides a new route to specify the no-boundary wave function, which in the long term might give us a more precise formulation of the wave function. Perhaps not even based on traditional notions of space and time.
We are most interested now, right, in learning how to compute, right, quantum mechanically what goes on in the early universe, irrespective of what the particular proposal is. How to get between the wave function of the universe, which is a fundamental theory, part of the fundamental theory, and predictions for observations. And that's a fairly hard thing to do. We can do that in a sector, if you like, of the wave function of the universe that's close to classicality, and there we think we know what we're doing. Susskind, Page, and other people speculate, right, that if we look for big quantum fluctuations, right, then we would predict more probable things that are not like what we see. We don't know yet, right? They might be right, but we have to develop our techniques of computation. In the meantime, we're making progress on how to compare things.
The aurora borealis is caused by electrons in the upper atmosphere being excited to higher energy levels. As they fall back down to their lowest energy level, known as the ground state, they give off light. This notion of a ground state is helpful to understanding how the no-boundary proposal explains many mysteries of physics.
The universe as we see it today was simpler earlier than it is now. More homogeneous, more isotropic, more nearly in thermal equilibrium. So you would expect it to be described, if there was a wave function, by the simplest possible wave function. In ordinary quantum mechanics, that's the notion of the ground state, the simplest possible state. Most ordered, most simple. The no-boundary wave function is the cosmological analog of the ground state for closed universes, and it seems to work.
When it comes to the arrow of time, the dynamical laws of physics are typically invariant and the reversal of the arrow of time. So the observed arrow of time must have something to do with the initial conditions.
The fluctuation started out small, right, and grew. Complexity, the universe started out simple and became more complex. Those are the basic features, right, of arrows in time. Complexity is increasing, and that can be quantified by appropriate entropies that also increase.
The regularity of the shuttlecock geometry implies that all fields are initially in their ground state. So the no-boundary proposal implies that when a classical universe emerges, this will be in a very much in its ground state, no structure. So it implies that the structures develop away from the Big Bang towards the future.
In one of our previous films, Sir Roger Penrose argued for a cyclic cosmology to explain the deep mystery of why the entropy was so low at the Big Bang.
The no-boundary proposal predicts that. So it may be a mystery, I think, to Roger, right, why the no-boundary proposal, but once you accept that, then I think you have arrows of time. Interesting enough, the no-boundary proposal predicts bouncing universes as well. Then it predicts arrows of time that are in one direction on one side of the bounce and the other direction on the other side of the bounce. If you have a bouncing universe that collapses, reaches a minimum, and grows, you might ask where are the fluctuations so small. It's not at one end, not the other end, it's in the middle.
Aaron Wall, a former student of Jim Hartle, has argued that the no-boundary proposal is not really a universe with a beginning, because the beginning only occurs in imaginary time. In real time, the no-boundary proposal implies a universe that is eternal to the past and future.
First of all, it's important to stress that what Wall means by real is not imaginary in the sense of fictitious, but imaginary in the sense of complex numbers.
It's a closure of the universe, so it's very much like a beginning of time. It happens in imaginary time, as Aaron says. You might wonder how that shuttlecock construction is connected to the histories of the universe in real time. You will typically find that the classical extrapolation of the history backwards in time exhibits a kind of hourglass structure. It's a sort of, you have a contracting phase going backwards in time, and then you have a kind of bounce, and you have another expanding phase on the other side of the bounce. So you might think, well, this is very different from the no-boundary proposal, but in fact it's not, because the no-boundary proposal predicts that near that bounce, all fields are in their quantum mechanical ground state, their minimum energy state. There's no structure near the bounce. The structure in those histories develops away from the bounce in both directions. That means that there is an effective arrow of time which goes away from the bounce towards the future, but on the other side of the bounce, the effective arrow of time goes the other way. That means that in those histories, there is absolutely no communication between both sides.
Many models for the early universe, whether they be derived from string theory, loop quantum gravity, or inflationary cosmology, seem to be converging on the idea that our expanding universe has a mirror image of itself, creating an hourglass-like structure for the cosmos.
I agree that this hourglass kind of picture of the universe is emerging from various angles now. But the natural initial condition will evidently make the early universe rather simple. And that automatically leads you to that hourglass kind of evolution with the arrow of time pointing in opposite ways of the bounce. Having said this, there are other proposals for cosmology, cyclic cosmologies or ekpyrotic cosmologies, in which there is clearly a distinction. Those proposals also invoke a sort of bouncing phase, but the arrow of time does not reverse. The arrow of time always goes forward. In other words, there is communication from the pre-bounce phase or the pre-Big Bang phase to the post-Big Bang phase. And eventually, I would imagine that both kind of proposals will lead to observationally distinct predictions and will be able to rule one of them out.
Alex Vilenkin has proposed a different quantum origin for the universe, where space and time tunnel into existence from a state of no space and time, similar to the way that virtual particles fluctuate from the vacuum. He claims this has a number of advantages over the no-boundary state.
Alex Vilenkin, who I know quite well, is a brilliant scientist, right? And we have to take seriously that we're not going to have a slam dunk theory of the wave function of the universe.
The no-boundary proposal will predict that we come from a regime of eternal inflation at a rather low value of the potential. Alex's wave function will predict that our universe emerges from a regime of eternal inflation that occurs at a high value of the potential. In these simplest dynamical models, I believe Alex's proposal is ruled out, because regimes of eternal inflation at a high value of the potential will naturally occur when the potential has a polynomial behavior. When the potential goes like the fourth power of the scalar field, for instance. But those kind of inflationary histories predict a large tensor-to-scalar ratio, which we don't seem to be observing. So I think Alex's proposal, for that reason alone, is under pressure.
So I would rather regard them as two separate approaches to the wave function of the universe, and we'll compete them on their predictions for such things as the large-scale structure.
The no-boundary proposal is a theory of cosmology developed before modern quantum gravity theories like string theory or loop quantum gravity were formulated.
String theory is a dynamical theory, and the no-boundary wave function is a very general idea that should apply to any theory of dynamics, or at least most of them, we hope. So you can put string theory into the no-boundary wave function and then check what it says about predictions. They're not separate. In fact, one of the beauties of the no-boundary wave function is, I mentioned earlier that contemporary final theory appears to have two parts, a theory of the quantum state and a theory of the dynamics. They're unified in the no-boundary proposal in the sense, given a theory of dynamics, you probably have something like a no-boundary idea.
In a way, the no-boundary wave function combines or unifies the theory of dynamics and the theory of initial conditions. And you can see this from this formula. Here's the theory of dynamics summarized by its action. And here are the initial conditions in one single formula. Together they define a wave function, and from the wave function you derive both the probabilities of different universes as well as their dynamical evolution.
The multiverse implied by the no-boundary proposal and inflationary cosmology may seem like a modern idea, but Georges Lemaitre, the father of the Big Bang, may have hinted at the basic concept as early as the 1930s in this quote.
Clearly, the initial quantum could not conceal in itself the whole course of evolution. The story of the world need not have been written down in the first quantum, like the song on a disc of a phonograph. Instead, from the same beginning, widely different universes could have evolved.
The no-boundary proposal is a model of the physical conditions at the beginning. It describes how our familiar notions of space and time can emerge from a quantum state of the universe.
There are certain questions that you simply cannot ask in the context of classical cosmology. An obvious question is, where does classical spacetime come from? Classical spacetime is assumed, obviously, in classical cosmology. But by deriving, so to speak, classical cosmology from an underlying quantum theory of the universe, you can ask in what regime and how classical evolution emerges. So you get a deeper layer of understanding of the basic building blocks, ultimately, of our universe.
In the no-boundary proposal, the same laws of nature hold at the beginning as in other places. The beginning of the universe would be governed by the laws of science. This removes the need for an intelligent creator. Ever since the dawn of civilization, people have craved for an understanding of the underlying order of the world. Why it is as it is, and why it exists at all. There ought to be something very special about the boundary conditions of the universe, and what can be more special than that there is no boundary. And there should be no boundary to human endeavor.